In this video we're going to look at simplifying radicals, and we're going to throw in some variables and exponents. So over here I have the list of all the perfect squares, so that if we take the square root of those they come out to be whole numbers, and some beginning of a list of perfect cubes, so that if we take the cube root of those they come out to be nice whole numbers. Well, if we throw in the idea of including variables and exponents, we need to start thinking about the square roots of variables and exponents. So let's throw an example problem up here, and then we're going to generate another list. Let's say we want to find the square root of x to the 8th and y to the 5th. Alright, well, my list over here doesn't really help me because I don't have any whole numbers. I just have variables and exponents. So let's generate a list like this that deals with exponents. So let's do square roots first. So the square root of x squared means what times itself is x squared. What times itself is x squared? Alright, that would be x. Now the next one in the list is going to be whatever comes out to be x squared. So think about this for a second. If you took x squared and squared it, x squared squared, I'll write that down and I'll erase it. X squared times x squared, what would you get? That would be x to the 4th. So that's going to go in here. That means the square root of x to the 4th then would be x squared. Let's look at the next one. What's going to come out to be x to the 3rd? What would have to go under there to have it come out to be x to the 3rd? Well, it would have to be whatever x to the 3rd times x to the 3rd is. What's x to the 3rd times x to the 3rd? X to the 6th, because you add the exponents, 3 plus 3. So hopefully you're starting to see a pattern here. The next one, I got to erase these. The next one we want to come out to be x to the 4th. So the square root of what is x to the 4th? What's x to the 4th times x to the 4th? Add the exponents, you get x to the 8th. So you can see what's happening here is we have even exponents. The square root of x to the 10th would be x to the 5th, because x to the 5th times x to the 5th is x to the 10th, etc. Alright, so let's look at our example. Well, we remember this rule from last time. We know the square root of a times b is the same as the square root of a times the square root of b. So that means we can split up this into two separate little problems and think of it as two separate problems. Now, as you get used to these, you might not write this step out. You may just think of it as two separate problems. I need to worry about how do I simplify the x to the 8th, and I need to worry about how do I simplify y to the 5th, and do them separately in your mind. Or you could write them out separately like this. So the square root of x to the 8th, since that exponent is even, it's going to come out nice. It's just going to be x to the 4th. What this is saying, what times itself is x to the 8th? And the answer to that is x to the 4th. Now this one, what times itself is y to the 5th? Well, because that's an odd exponent, it's nothing. Nothing times itself is y to the 5th. So what you have to do is similar to what you do when there's a number. You have to break this apart. Whoa, that was weird. I don't know why that did that. You have to break this apart. So what you're going to do, this works every time it's a square root, okay? If you have an odd exponent, you basically subtract 1 and of your exponent, so change that 5 to a 4, and then pull that 1 off to the side over here. So in other words, y to the 4th times y is y to the 5th. You're just going to pull one of them out, so that's going to leave you an even number of y's. Alright, so why do I do that? How come I did that? Because y to the 4th, I can take the square root of y to the 4th. So I have the square root of y to the 4th. I'm splitting them apart now, and a y. My x to the 4th is going to come down. Now I can take the square root of y to the 4th, which is y squared. What times itself is y to the 4th? That's y squared. Basically, all you're doing is you're dividing the exponent by 2. Hopefully you saw that up here in this pattern. Right? 6 divided by 2 is 3. 8 divided by 4 is, or 8 divided by 2 is 4. 10 divided by 2 is 5. And then this square root of y, since he's only one y, or y to the first power, he can't come out. You know, you got to have at least an x squared. You got to have at least an exponent of 2 to get out of that square root. So he's trapped in there, and that makes our final answer. Okay, that would be your final answer, as ugly as it looks. That's it. Let's try another example. Maybe you can, if you think you got a handle on it, pause the video and try it on your own. Let's try the square root of, let's go a to the 16th, b to the 20th, and c to the 15th. Alright, if you want to give it a try, go ahead and pause. Alright, so if your exponent is even, you're home free, because all you have to do is divide it by 2 to take the square root. Remember, you're thinking of this as 3 separate problems, and you don't necessarily have to break this out. Well, your instructor might want you to. I don't know. You got to ask them. Now, the c to the 15th, that's odd. I need the exponent to be even, so the even number closest to 15 is 14. I want this to come out to be c to the 15th, so c to the 14th times c is c to the 15th. That's what I was talking about before. You just kind of pull one of them out, one of those c's, and then you times it by however many are left, which is c to the 14th. Now I can take the square root of a lot of stuff here. The square root of a to the 16th is a to the 8th. Just divide the exponent by 2. The square root of b to the 20th is b to the 10th. The square root of c to the 14th is c to the 7th. And then this little c right here, he has to stay inside the square root. There you go. That's all there is to it. I mean, once you get the hang of it, it's not too bad, because you're just dividing by 2, basically. Now, we could stick a number in there with this. Here's a tricky one I like to give. Let's say we had the square root of 8x to the 8th. The square root of 8x to the 8th. Now you have to treat the coefficient 8, the big 8, differently than the exponent 8. So the big 8 right here, we have to use this list here, our perfect square list. Are there any of these numbers that go into 8? Yep, 4 goes into 8. So we'll split up the 8, the big 8, into 4 times 2. And the x to the 8th, that's a perfect square, so I don't have to worry about him. Now I'm going to write this a little bit differently here, kind of showing how to skip a few steps. Once you break this apart, you just look underneath that square root and say which one of these factors are perfect squares. That 4 is a perfect square, and that x to the 8th is a perfect square. That means I can take the square root of them. They're gonna come out. And to get out, I have to take the square root. So the square root of 4 is 2. The square root of x to the 8th is x to the 4th. And then this 2 right here, he has to stay. He stays in. Alright, let's try another one. Let's try another one. How about the square root of, let's put a number with some variables in there. Oh, let's go 75 x to the 2nd, y to the 9th. If you think you got a handle on it, go ahead and pause the video and give it a try. Alright, so 75, the 75, I need to look in this list. Are there any perfect squares that go into 75? 25, I think, is my my factor I want, because 25 goes into 75. So 25 times what is 75? Well, that's going to be 3. X squared, that's an even exponent, so I don't have to worry about him. He's good to go. Y to the 9th, that's an odd exponent. So I need to subtract 1 from that, change it to an 8, and then put that 1 there. So everything's accounted for. See, if you multiplied all this stuff back together, you'd get what you started with. Y to the 8th times y is y to the 9th. That's really, really important. You want to look and make sure you haven't forgotten anything. Y to the 8th times y is y to the 9th. Your x squared is there, and 25 times 3 is 75. But by breaking it apart like we did, we've created some perfect squares here. X squared was already a perfect square that we can take the square root of. Alright, so the square root of 25 is 5. So you don't put a square root sign over it anymore because you took the square root of it. He's out. The square root of 25 is just plain old 5. The square root of x squared is x. Notice I skipped over the 3 because I can't take the square root of 3. Well, without making it a decimal. Keep my color coordination here. The square root of y to the 8th is y to the 4th. And then what do I have left in the square root? Well, I got this 3 here. He's still underneath there, so I got to bring him down. And I still have this y. Those are the two guys that are left inside because they weren't perfect squares, so they had to stay inside. So there's your final answer. 5x y to the 4th, I'll write it a little nicer, 5x y to the 4th times the square root of 3y. So there's a lot of stuff going on, but you really need to just break it down and look at it as smaller problems. Can I take the square root of 75? Can I take the square root of x squared, etc.? Alright, let's go ahead and look at a cubed root. I'm going to erase, what do I want to erase? I'll erase these. Alright, so for cubed roots, it's a little bit different. Let's say we wanted to do the cubed root of, how about 27 x to the 6th, y to the 12th. We'll do an easy one to start. Well, a nice one. Okay, so these perfect squares with the x's don't really help us. We need perfect cubes now. So the cubed root of x to the 3rd is x. The cubed root of what would give me x squared? So to figure that out, you need to think of what is x squared times x squared times x squared, because we're doing cubed roots now. So x to the 2nd cubed would be, add the exponents, x to the 6th. Let me erase this so we have room. Now notice, it's the same kind of idea with the dividing. 6 divided by 3 is 2. Just like we were doing over here. Now this index is not written, these square roots, but there is a little 2 there. We don't write it. I'll write it in red, but it's not usually there. When it's not there, it means a square root. The index is 2. 10 divided by 2 is 5. See the same patterns going on over here. Alright, so cubed root of what would be x to the 3rd? So 3 times 3 is 9. X to the 9th. 9 divided by 3 is 3. The cubed root of x to the 12th is x to the 4th. Because x to the 4th times x to the 4th times x to the 4th is x to the 12th. See the pattern? Now we're going by multiples of 3. 3, 6, 9, 12. The cubed root of, hopefully you get the next one, x to the 15th, x to the 5th, etc. So this problem I made up over here, like I use the word easy, which I don't usually like to word, but less complicated, because our exponents are multiples of 3. They're in our list, x to the 6th, and I used a y, but it doesn't matter, x to the 12th. So those are going to be nice to take the cubed root of. And the 27 is in our list of perfect cubes right here, the cubed root of 27. So the cubed root of 27 is 3. The cubed root of x to the 6th, you just divide those, 6 divided by 3 is 2. And the cubed root of y to the 12th is y to the 4th. Because y to the 4th times y to the 4th times y to the 4th is y to the 12th. Now I want you to be really careful with this dividing thing I'm talking about. That only works with the exponents. Notice I did 6 divided by 3 to get 2 and 12 divided by 3 to get 4. I didn't do 27 divided by 3 to get 9. Okay, it only works with the exponents. And the reason it works is because of the rules of exponents. We know x squared to the third power, the way we simplify that is to multiply the 3 times the 2 and get 6. So when you're taking something to the third power, that's sort of the opposite of doing the cubed root. If I do the cubed root of x to the 6th, that's undoing a cube. If you cube x squared, you get x to the 6th. If I do the cubed root of x to the 6th, I'm undoing what I just did. I end up with x squared. So because you multiply these to get that exponent, then you're going to divide these to get that exponent. That's why you do the multiplying and the dividing with the exponents. But don't do that with the whole numbers. That's not the situation with the whole numbers. The cubed root of 27 is 3 times 3 times 3, so the answer is 3. 3 times 3 times 3 is 27, so the cube root of 27 is 3. You have to really treat those differently. So I could, do a trick question. This would be a trick question that I might give. I might say the cubed root of 27 x to the 27th. Just to see, does the student understand I have to treat these two 27s differently? This is a big whole number 27. What's the cubed root of 27? 3. This is an exponent of 27, which is different. So I have to divide the 27 divided by 3 to get 9. See, those 27s come out to be different things when you take the cubed root of them. Now, what if I don't have something that's divisible by 3? Let's say I don't have an exponent that's divisible by 3. Let's say I have the cubed root of x to the 10th. Okay, 10 divided by 3, that doesn't work. Well, what you want to do is you want to split this up into the exponent that's as close to 10 without going over, that's divisible by 3. So just look in your list here. It looks like 9. So in other words, just go down. 10, 9, 8, 9. Boom, that's divisible by 3. Okay, so the cubed root of x to the 9th would be x to the 3rd. 9 divided by 3. And then this guy is going to stay in here like that. So if you had the cubed root of x to the 11th, you'd still have to go down to 9. But then you'd have x squared left over. So x to the 9th times x to the 2nd is x to the 11th. That works out good. Everything's covered. Then I can take the cubed root, of x to the 9th, which is x to the 3rd. And this guy is left inside. Cubed root of x squared is left inside. It's kind of like dividing with a remainder. I mean, that might be another way to think about it. 11 divided by 3. 3 goes into 11 3 times. That's why you have this x to the 3rd out here with how many left over? 2. So you have an x squared left over inside the cubed root. Alright, let's give you one more to try with the cubed root. And maybe pause the video and see if you can make this work. I'm not going to get too tricky with the numbers. Let's do 64 x to the 14th y to the 3rd. Alright, pause the video and give that a try. Alright, so this cubed root of 64, I'm looking in this list. That's easy, right? That's right here. The cubed root of 64 is 4. That comes out nice. So that one's good to go. The x to the 14th, 3 doesn't go into 14 nice. 3 is going to go into 14 4 times. So here we go right here. The closest multiple of 3 is going to be 12. So I want to split this up. I'll just take a step and split this up. 64 is good. I'm going to leave that. X to the 14th, I'm going to change that to a 12. So that's divisible by 3. And that's going to leave me 2 left over to make my 14. And y to the 3rd, that's certainly divisible by 3. So I'm good there. So it looks like I'm going to be able to take the cubed root of everything except for the x squared. That guy's good to go. That's good to go. That's good to go. And then what's going to be left inside on my next step, the only thing that's going to be left inside is this x squared. So let's write what we have out here. The cubed root of 64 is 4. The cubed root of x to the 12th is x to the 4th. And the cubed root of y to the 3rd is y. Alright, well hopefully that helps, and once you get the swing of it, they're not too difficult. This is really the key, and I wrote all these out, and we referred to them a lot. But hopefully you can see with the cubed root, you're just looking at multiples of 3 for your exponents. For square roots, you're looking at multiples of 2 for your exponents. And you know, if you get stuck on a test or a homework, just write a few of these out, make a few of these lists, and I think that'll really help with figuring out how to split these up.